Recently in class we talked about optics and how we can use lenses and mirrors to manipulate light. And today we're going to talk about telescopes, which are systems that we build with those lenses and mirrors to study space. So today's lecture is all about telescopes. If you put multiple lenses, or as we'll see, mirrors and lenses together, then you can make different optical systems. So for astronomy, we make telescopes so that you can see faraway objects in greater detail. But in other types of sciences, we can put lenses together to make microscopes where we can see very small objects in greater detail. Okay, so the physics behind this, so we'll go back to our what we talked about with lenses last time. So if I have an object that's really far away, like some star in space that we're looking at, the distance from my lens to that object is, so this is my object distance, and that's we're going to approximate that to be infinity. So it's infinitely far away. So putting in 10 or 100 or 1,000 light years, when you do the math, you can just put in infinity. So that the light from that object is going to hit this lens, and then that lens is going to make an image behind it. The distance from that, so this is going to be called the objective lens, because it's the one closest to the object. The distance from the objective lens to the image is the image distance, and I'll call that image distance 1, because we're going to end up with 2 images. And if we remember the thin film or thin lens equations from last time, one over the focal length of this lens is equal to 1 over the object distance plus 1 over the image distance. But if we plug in infinity for the object distance, 1 divided by infinity just goes to 0. So this term just goes to 0, and you're left with 1 over focal length equals 1 over image distance, and so that just means the focal length is equal to the image distance. So where this image is going to be produced is just dependent on the focal length of your objective lens. Okay, so now I've looked at something far away, put the light through this objective lens, it made an image behind it. Now this image is going to be the light that we're looking at through our eyepiece lens. And so now you can pretend all of this original stuff didn't matter. Now we just have light from something hitting our eyepiece lens, and then we do the process again. So now for the eyepiece lens, my image is going to be my new object. That object is going to put light through the eyepiece lens, and then the light will be manipulated by the properties of the lens, and then it will make another image on the other side. So you could call this image 2. And so if you wanted to, you could do another one of these thin lens equations, where now this distance, I'll call it be image 2, so that would be here. And then the distance from the image to your eyepiece lens is, maybe we'll call that D object 2. So the first lens makes an image, and then that image acts as the object for the second lens. And you can use all of these equations to do your calculations to figure out how far away do I need to put two lenses together in order to make something like a telescope. So that's the general principle for why putting two lenses together works and the physics that goes into that. So this is just, again, so this is the second step, right? So the image is now producing my light for the eyepiece. The eyepiece lens has some focal length, and depending on where the image is with respect to the eyepiece lens, you can magnify your images, and you can do all of the calculations you need to figure out where to put, like what distance these two should be apart so that you get a bigger image. So the whole point of putting these multiple lenses together is we want to make something that's very far away and small a lot bigger so we can study it in greater detail. So the magnification for a telescope is going to be calculated by taking the angular size of the object in the telescope and comparing it to the angular size of the object on the sky. So for example, when we look at the moon with our naked eye, the size, does anyone remember what size the moon was, roughly? It's about half a degree on the sky. So if you look at the moon through a telescope, you can magnify that angular size from being, instead of say half a degree, maybe now it's 10 degrees in your telescope. So you would take 10 divided by a half, and that would give you a magnification of 20. So that wouldn't be a very big or strong telescope, but it would allow you to see 20 times more detail on the moon than you could originally. So that's how you would calculate the magnitude if you had the angles you were looking at. If you were just looking at the optical system, then you would look at the focal length of the objective lens and the focal length of the eyepiece lens. And so the negative sign is not telling you that the magnification is smaller, it's telling you that the object will get flipped upside down in your telescope. So that's the trade-off that we have, is when you magnify, if you want to magnify the image is going to end up being upside down. So just be wary of that when you look through a telescope. And so if you want your magnification to be bigger, then you need your objective lens to have a bigger focal length than your eyepiece lens. Kind of a brief intro to how the physics works, and now we'll get into what we can study with telescopes and why we put them where we do, and then at the end we'll talk about other types of information we can get from space that isn't just from light. So why do we use telescopes? There's several different reasons. So one of them is we can make telescopes that are bigger than our eyes. So the bigger telescope you have, the more light you're able to collect from that object. And then we've talked about how you can see something in greater detail, so that's increasing the angular resolution for the object. Our eyes are only sensitive to visible wavelength light, but we'll talk about different kinds of telescopes that we can design to see all across the electromagnetic wavelength ranges. And then recently we've developed sensors that can, instead of just taking the amount of light that hits the telescope in one instant, you can collect photons over a long period of time, potentially hours at a time, and so you get a much deeper or more sensitive measurement than if you were just looking through the same telescope with your eye. When you're building a telescope, bigger is better. The bigger the area of your telescope, the more light you're going to collect. So you can think about a telescope as just a bucket that catches all of the light that's hitting it. And we usually design telescopes that are circular, and so the area of your circle is going to increase as the radius squared. If you have a bigger telescope, you get better angular resolution. So if you're trying to study, say, craters on the moon, a bigger telescope will allow you to see smaller craters. And then when we talk about, if I say, for example, the telescope we have at the observatory is a 16-inch telescope. That number that I'm telling you is the diameter of its biggest mirror or lens. So there are some very large telescopes that we've built. So this is the Keck telescope in Hawaii, and you can see a tiny human in front of this telescope for scale. And then this is me in Chile in front of the Blanco 4-meter telescope. So that means that the size of the mirror, which is down here somewhere, is 4 meters in diameter. So that's a little more than 12 feet across. And for example, for Keck, it starts to get really hard to build a solid piece of glass that's 4 meters in diameter. So we started building these hexagonal like little sub-mirrors that all work together as one big mirror. And these actually have an advantage to a solid piece of glass that we'll talk about towards the end of the lecture. Okay, so let's say you wanted to upgrade your observatory's 1-meter telescope. How much larger is the collecting area for a 2-meter telescope? So remember so 1 meter is telling you the diameter of the circular mirror. Then the 2-meter telescope would have a diameter of 2 meters. But the area is pi r squared. So the area for a 1-meter telescope would be 3.14 times 1 squared, so that would be 3.14 meters squared. And then for the 2-meter, pi r squared, pi times 2 squared. So now you have 4 times 3.14, so that's 12 point something. What's 14 times 4? 64. So then if you're comparing the two areas, we'll call this area 1 and area 2. .64 divided by 3.14, and you get 4 times. So that's the long way to do that calculation. The other thing that you could do, if you do everything in variables first, so if I'm doing area 2 divided by area 1, that's pi r squared divided by pi r squared. My pi's cancel, and now I'm just doing 2 squared divided by 1 squared, which is going to give me 4. So the takeaway for this is that the doubling your diameter of your telescope will 4 times your collecting area. So, very useful to make your telescope as big as possible. And so this is the largest refracting telescope, and refracting telescopes are ones that are only made out of lenses. So this is the largest refracting telescope in the world, the Yerkes 1 meter refracting telescope. And so you can see the person for scale, and you can see how long the tube has to be in order for this refracting telescope to work. The objective lens is the front one, and this is the 1 meter lens. So the diameter of this tube at the top is 1 meter to accommodate this 1 meter lens. And the telescope has to be so long because it takes a long time or a lot of length for that light to become focused and then hit the eyepiece lens so that it will be something that you can look through or put your detector at the bottom of. So this is kind of the limit you can get to with refracting telescopes. With reflecting telescopes, so if we start to use mirrors, we can make the telescope tube much shorter. And that's because the light can bounce off of mirrors, and you can basically cut the distance the light has to travel in half or more. Because the time it would take for this light to focus, instead of going down one long tube, now the light can bounce back and forth in a much shorter tube and still have be focused. And you can actually get bigger size telescopes by building them as reflecting telescopes, because the light's able to bounce back and forth and reduce the tube length that you need to put all your optics in. And so most telescopes that are going to be designed today are going to be some type of reflecting telescope with mirrors as their objective optical component. There's a lot of different types of reflecting telescopes. Some of them are good for looking through, some of them are not. So this prime focus reflecting telescope, the light's coming in from the left, hits the primary mirror, and then it's focused at some point in the middle here. So this works if you have like a detector that you want to put here. But you could imagine if you're a person and you try to put an eyepiece where this prime focus is, you would be blocking most of the light coming into the telescope. So this design doesn't really work for people viewing. And so there's other designs that have been developed so that you can either look through the telescope or put a detector on it. So the Newtonian, named after Newton, you've got your mirror, primary mirror reflecting the light coming in, then it gets bounced off of a secondary mirror and off to the side, where you can then put your detector or eyepiece. Cassegrain. Now we've got our primary mirror, and then our secondary mirror is actually a convex mirror that puts the light back through an opening in the base of your primary mirror. And then the last type is similar to a Newtonian, but we stick an extra mirror in there. So there's lots of different ways you can think of to have light bounce off of mirrors and then focus on a point for either an eyepiece or a lens. You can also design systems where you combine mirrors and lenses together. So these are called catadioptric telescopes. And these are the types of telescopes that we have at these are the smaller telescopes that we have at the observatory on campus. So for some of them you have light coming in that's focused on some primary mirrors, or not mirrors, primary lenses. Other ones, the light comes in, bounces off a primary mirror, then a secondary mirror, and then is sent through lenses. And then this one's interesting because you have the front side of this is a lens that focuses on a back mirror and then off of another mirror and then into the eyepiece. So again, there's just lots of different ways you can think of combining lenses and mirrors to make useful telescopes. Those are mainly designs for optical telescopes, so things like visible wavelength light, a little bit of infrared light, and some ultraviolet light. But when you want to look at other wavelengths, you need to use other kinds of technology. The main barrier is for whatever wavelength of light you're trying to observe, your primary mirror, or in this case a dish, has to be at least as big as the wavelength of light you're trying to study. So for visible wavelength light, you're in the hundreds of nanometer range, so it's really easy to make a piece of glass bigger than that. But when we're talking about radio waves, you could be trying to study radio waves that are meters long. And so you need to design a system that's bigger than meters long. And if you want better resolution, your telescope has to be several times bigger than the wavelength of light you're trying to study. So when we're trying to study radio waves, we need these huge dishes to collect those radio waves. So this is the 500-meter radio telescope in China, and so that's 500 meters as the diameter for this dish. And at that scale, it doesn't make sense to use mirrors or glass, so this is just concrete. And the radio waves will bounce off of the concrete or get focused where we want them to get focused. And then I mentioned that we've developed new technology to attach to our telescopes to collect light. So originally, people using telescopes just looked through the telescopes and had to make note of the observations they made. Then in the 1900s, people developed photographic plates. So if you're familiar with how film photography works, kind of a similar process where you put some kind of chemical that will react to light as you're either on a film or on a photographic plate, And when that chemical is exposed to light, it will react and leave an image of what it saw. But now we use a completely different type of technology. So what we use now is based off of the photoelectric effect, which is actually what Einstein won the Nobel Prize for. He did not win the Nobel Prize for special or general relativity, so that's a useful trivia knowledge. What the photoelectric effect says is that for things like a metal or a semiconductor, different frequencies of light will hit that semiconductor and will release a photon. So it's similar to what we talked about with gases when we were talking about spectroscopy, but this is for solid objects. And so if you find the right kind of chemical structures, you can design systems that will react to, say, visible wavelength light or infrared light. And so when the correct type of light hits this photosensitive region, it will release an electron, and that electron is something that you can read with an electronic system. So if I have electrons now that are starting to move around, that'll generate a current, and I can measure currents with techniques that you could learn about in a physics class. So at each pixel on a camera, you'll have this kind of system, and then you build up what an image looks like by combining all of the pixels in the camera. So this is what we use now to put on our telescopes to study space. For higher energy photons, it becomes much harder to deal with and constrain those photons. So conventional optics do not work well for X-rays. So X-rays have high enough energy that if you just tried to have a mirror perpendicular to the path of the X-ray would just pass right through the mirror. So that's why X-rays are good for medicine, is they pass right through your soft tissues and bounce off your bones, so we can see what your bones look like on the inside. But that makes it hard to design a telescope, so instead of having the X-ray hit at a 90-degree angle, we have these grazing incidence optics. And so instead of using a perpendicular mirror to direct the X-rays, we have the series of grazing optics that will, so the X-ray isn't hitting at a 90-degree angle, it's hitting at a much shallower angle, thus allowing the X-ray to not pass through our mirror, but instead get deflected by small angles and then eventually focused on our X-ray detector. So developing these X-ray systems will lead to a Walter telescope. So those are the grazing incidence X-ray telescopes. And then gamma rays are the highest energy photons, and they're even harder to deal with. So we don't really even bother trying to make optical systems to study these things. And instead, there's two different phenomena that we can use to try to detect gamma rays. So the first are indirect detections. And so what you'll do is you'll design a scintillating crystal. So these have certain chemical properties where when a gamma ray photon hits them, they will emit visible wavelength light. So there's some kind of physical and chemical reaction that goes on inside of this crystal when it's hit with a gamma ray photon, and that causes it to emit light in optical wavelengths. Then you just set up a normal optical wavelength detector to basically stare at these crystals and wait for them to start glowing. And then you do a bunch of complicated physics to work backwards and figure out where that gamma ray had to originate in the sky. The other way we can look for gamma rays is by Compton scattering. So if we have an atom that's hit with a gamma ray photon, if that photon happened to hit one of the electrons orbiting that atom, it will knock the electron out of the orbit around the atom, and then we can try to measure this signal of the electron moving, which generates a current. So this is harder to do, but we'll see this kind of technique in a little bit when we talk about other types of information we can gather from space. Okay, so why do we put telescopes into space? It's not because they are closer to the stars we're trying to study. So earlier in the semester we talked about this scaling, where if we scale the sun down to the size of a grapefruit, that would make the Earth about the size of the tip of a ballpoint pen, and the distance between the Earth and the sun would be 15 meters, but the nearest stars would be 4,000 kilometers away in that model. So putting a telescope into space is like microscopically getting closer to those nearby stars. So we're not doing it because we get closer to the stars. We're doing it for a few different reasons. So when we look for the best places on Earth to put telescopes, what we're looking for are very dark skies, so not a lot of light pollution, so not near cities. High altitudes, because you have less atmosphere to look through, and we'll talk about why the atmosphere is a problem. You want a dry climate, because if it's rainy all the time, then you're not going to be able to see through the clouds, and then you want people to be able to get there. So even if the weather on Mount Everest was nicer, that might not be a good place to put a telescope because it's too high for humans to comfortably exist and carry out science experiments. So the biggest problem is light pollution. So you can see kind of a scale here of, in a big city you might not even be able to see stars, and then as you get into less and less populated areas, you can see more and more objects in the sky. So where we are is kind of, I would say, in the 5 range. And then if you drive out of town a little bit, then you might be able to start seeing the Milky Way. There's a story, I don't know if it's true, but in Los Angeles in the 90s, there were really bad blackouts. So all of the city lights went away, and there were people calling 911, reporting UFOs in the sky because they were seeing the Milky Way for the first time. And then this is a map of the brightness of the sky, at least for the eastern half of the country. So even a small town like this, we still are red. So not very good with regards to light pollution. So you can see if you can get out into the blues, then you're going to get really dark skies where you can see the Milky Way with your naked eye, and those are good places to build or bring your telescope. The gray parts are just, there's not enough data to say what that brightness is, but it's probably fairly dark because there's not going to be a lot of towns out there. Okay, so maybe take a couple minutes amongst yourself to think about ways that we could make the night sky darker. have any ideas they would like to share? Yep.
Especially at night, dim, artificial lights.
Yeah, so you maybe, so dimming existing lights. Anything else? Yep.
You know, in some cities, street lamps, they have like rings around them so the light only faces
Yeah,
down.
so directionality. Anything else? Yeah, so those are good ideas. So the two that we're going to focus on really are just how you point your lights. So certainly in cities, we've decided that at night we want some lights, either for advertising or for safety reasons, but there's smarter ways that you can do it. So this example for the billboard, normally you just see billboards lit from the bottom, and that does a good job of showing the text on the billboard, but then the light's either bouncing off of the billboard and going into the sky or just going straight into the sky. So you're making the skies much brighter unnecessarily. Because you could also just have your lights on top pointing down. You still get the same brightness on your sign, but you're not polluting the skies with extra light. And then street lamps are another good example. So you can have just a circular street lamp that emits light in all directions, and that will illuminate the ground. But you could also just as easily put something that points the light straight down, and then you're not getting as much light pollution into the sky. So these are just a bunch of different examples of light fixtures that have some kind of cover on the top or are pointed downwards so you don't pollute the sky with a bunch of unnecessary light. And so this is just for my own curiosity, would you vote for or advocate for some kind of outdoor lighting ordinances that would reduce light pollution? Good answer. Okay, so now we're going to talk about why we want to put telescopes into space and what problems the atmosphere causes. So this is the same star as viewed from a ground-based telescope and as viewed from Hubble. So the atmosphere is not a steady thing that we're looking through. The atmosphere is turbulent. It's always, the particles in the atmosphere are always moving. And so when you're trying to look through that, it can blur your images. So that's one of the reasons we put telescopes in space. The other reason is that for some wavelengths of light, the atmosphere is going to absorb that light. So gamma ray photons and X-ray photons don't really make it through the atmosphere. Ultraviolet don't make it through the atmosphere either. And even some infrared light doesn't make it through the atmosphere. So if you want to study space in those different wavelength ranges, then you're going to need to get above the atmosphere, which means launching your satellites into space, or your telescopes into space. So Fermi's a gamma ray detector, Chandra's an X-ray detector, Hubble's visible. So even though visible light does make it to the Earth, we saw that the turbulence of the atmosphere makes it useful to have a visible wavelength telescope in space. James Webb is an infrared telescope that's in space, and Planck is a microwave detector that's in space. So going into space solves the problem of light pollution, turbulence in the atmosphere, and the atmosphere blocking certain wavelengths of light. So if you can overcome the cost, then it's very beneficial to put your telescope in space. So this is a picture of the Hubble Ultra Deep Field view. And so besides these two stars that have the kind of spikes coming off of them, everything that you see in that image is a galaxy. And some of these are very, very far and very, very old galaxies. And we would not get this kind of picture from a telescope on the ground. So James Webb is the newest big telescope from NASA, and it's currently in operation, and it's observing in infrared wavelengths. So here's a video of its the sequence that it went through after it got to where it is in orbit. So this is how it launched, and then it had to basically unfold to start taking data. So those kind of foil-looking things are heat shields to protect the instruments from the sun. If you have an infrared detector, it's going to be very sensitive to heat, and so you need to block out the heat from the sun and stop your instrument itself from heating up in order to get useful data. And the telescope needed to be folded up like that in order to fit into the rocket that sent it into space. There are some techniques that we can use on the ground to overcome the turbulent atmosphere. So that technique is called adaptive optics. And so on the left you can see what you would see without adaptive optics through a telescope, and then with adaptive optics, this blob is actually two stars that are orbiting each other. And the way adaptive optics works, especially for those telescopes that are the individual hexagons that are all working together, is you can have little pistons behind those hexagons that will slightly change their angle and orientation to react to the turbulence of the atmosphere. So you basically deform your telescope slightly to take into account the changes in the atmosphere. And so you can see Neptune without adaptive optics and with adaptive optics, and then Jupiter's moon Io without adaptive optics and with adaptive optics. So on Neptune you could see actual cloud structures on the surface, and for Io, you can actually see individual volcanoes on the surface using this technique. You've probably seen large arrays of telescopes, and that works on the principle of interferometry. So the goal is to build the biggest telescope that you can, but that's not always economical or feasible. So instead, you can have many smaller telescopes all pointing at the same object, working together, and that will give you an equivalent resolution to if you had a telescope that was as big as all of these put together. So which of these is a reason to launch a telescope into space? And there might be multiple correct answers. Yeah, so you want to avoid the atmosphere absorbing some of the photons that you might want. There's not going to be a rainy day in space, and there shouldn't be a bunch of light pollution from a nearby city. So it's not because we're getting closer to the object of interest, because the distance from the ground to space is very small compared to the distance to that interesting astronomical source. We talked about telescopes and how we can design different telescopes to study different kinds of light, whether that's visible wavelength, ultraviolet, gamma rays. But it turns out that light isn't the only thing that we can study from space. So there are other particles or waves that we can detect, one of them being neutrinos. So these are subatomic particles that are produced in fusion reactions, and when we learn about stars, we'll learn about their nuclear reactions and the role that neutrinos play in those reactions. The other thing that we can study from space are cosmic rays. So these are very high energy subatomic particles like protons and electrons that are coming from somewhere in space and hitting the Earth. And then very recently, within the last 10 years, we've developed the technology to study gravitational waves. And so these are Einstein's general relativity altering the fabric of space and time, and we have detectors that can measure that distortion. So the first type of experiment we'll talk about are neutrino detectors. And so neutrinos do not interact with regular matter very often. So they don't have an electric charge, and they have very low mass. So they don't interact gravitationally or electromagnetically. So how do we detect them? We just put an optical detector, so that's what this spherical thing is in the bottom right, inside of some medium and wait for a neutrino to accidentally bump into one of the atoms or electrons in the material. So in the case of ice cube, the material chosen is the Antarctic ice. So you drill a bunch of holes in the ice in Antarctica, and you string these spherical detectors throughout the ice, and if you have a large enough volume of material, then eventually a neutrino is going to accidentally bump into one of the atoms in the ice, and when it does that, it's going to emit a photon in the visible wavelength range that these detectors can detect. Then you do a bunch of high-level physics to calculate backwards to see what part of the sky that particle had to come from. And so you can see in this picture the Eiffel Tower for scales. Eiffel Tower for scale. So these holes are drilled very deep into the Antarctic ice. So we have ice cube. There are some other neutrino detectors that use water instead of ice as their material, and you're just waiting for a neutrino to bump into some particle in your material. We've mentioned shrink-off radiation before. So if you have a particle that's traveling faster than light in air, so remember the speed of light in the vacuum is the highest speed that something can travel. But in a fluid like air, the speed of light is not the fastest speed anymore. And you can get things like cosmic rays traveling faster than the speed of light in air. When that happens, you get shrink-off radiation. So that particle will start to emit a blue photon, and it will emit those photons until it slows down enough that it matches the speed of light in that medium. And then these detectors are built to look for that blue photon, and then again you can do some high-level physics to calculate backwards from where that photon was detected to where it must have come from in space. And then the last type of observatory that we've come up with is to study gravitational waves. So electromagnetic waves travel through space in 2 dimensions. When the electric field oscillates in one direction, the magnetic field will oscillate in a direction perpendicular to that one. That's a dipole. That's called a dipole moment. Gravitational waves will oscillate through space in what we call a quadrupole moment. So what that means for how we can detect them is as they propagate through space, if you had some circle hanging out in space and a gravitational wave passes by it, then part of the circle will be stretched out, but the other part will be compressed. And so you get these different lengths that you can measure. And so what scientists have come up with is what's called a gravitational wave interferometer. So you shine a laser down these 2 very long tunnels in the ground. You have a beam splitter at the beginning of both of these long arms. And so the laser light is going to be split, and if there were no gravitational waves, the time it would take to travel down each of the legs and return back to where it was split would be the same amount of time. But if a gravitational wave goes past, one of these arms can be lengthened and the other one can be contracted, and so the time that it would take for this light to travel down the arms of the interferometer is now different. So by measuring a difference in the length of the arms of your observatory, you can detect the gravitational wave. So there's 2 of these in the US, there's 1 in Italy, and there's 1 in Japan. So using all of those working together, you can again do some very high level physics to work backwards to where those gravitational waves must have come from in space. And we'll come back to talking about gravitational waves a bit at the end of the semester when we talk about big explosions in space like supernova and gamma ray bursts. So those are the 3 big things we can study from space that are not light. And so here's some examples of what that quadrupole moment for a gravitational wave might look like. So this is the result of 2, the one on the left is the result of 2 objects spiraling in towards each other, which is what you're going to see a lot in astronomy. And again, we'll come back to that later in the semester. So telescopes let us see fainter objects than we could see with our eyes, and we can develop telescopes that let us see in not just visible wavelength light, but across the electromagnetic spectrum. And then as we just saw, we're not just constrained to study light, we can study neutrinos, cosmic rays, and gravitational waves. And if you really want the best data, you need to put your telescopes in space.